Hello and welcome to my video on NES sprites, or OAM as they are known on the Nintendo. So I'll first give you a quick overview of their powers and attributes, and then I'll show you the demo that I've created, and then we'll dive into the code, which you can obviously use in your own programs to play around with sprites. So to start off with, there are 64 sprites in total on the NES. So a sprite is basically an 8x8 pixel image or an 8x16 pixel image. Those images appear as a layer on top of the normal background tiles, but they can be moved over the screen in 1 pixel increments and move more smoothly than tiles can be plotted. So each sprite takes up 4 bytes of RAM. They consist of their horizontal position, vertical position, the tile ID. So the tile ID can only be between 0 and 255. And there is also an attribute byte. So you can also mirror the tiles horizontally or vertically, and each tile can have 4 colours, although only 3 will ever be visible. The first colour in the palettes of the sprites are always invisible. And the order that the sprites are in the sprite table, which is basically an array in 0-page RAM on the NES, which has to be connected to the PPU so that each update the PPU will then use that array to draw the sprites on the screen. So the attribute bytes consist of bit flags, as we can see here. So bit 0 and 1 control the 4 palettes that you can use. So the palettes are considered to be palettes 4 to 7, which I'll kind of show you when we get into the code with GBDK shortly. Then there's a priority flag here, which allows you to have your sprites go behind the background or in front of it. By default they're in front of the background. And then bits 6 and 7, if set, flip the tiles horizontally or vertically. All the details here you can find at the nesdev.org wiki under the PPU OAM part. So I will now get into our demo here. So here we go. We've got our main sprite here, Yoshi, with a set of wings so he can flap around. You can move him around with the joypad, and it also shows off a number of other sprites as well. So there's an array of sprites there moving around. So the sprite manager code which I have is set for creating 16x16 sprites, as in the image sizes, and then the screen itself is set into scroll mode. By that, that means that the left hand margin here is not drawn, which allows you to seamlessly move sprites in and out of the border there. and also there's a setting which stops the sprites being offset by 8 pixels to the left, which means that you can move out of the right border nicely as well. As the sprite's horizontal position can only be between 0 and 255. Normally there would be issues trying to transit the screen there, but because of the settings with the margin on the screen, it allows them to move nicely out of the borders and in the other side. So another thing I've got here as well is the background, which is consisted of just a few tiles reused to create the scrolling scene. So if we have a look at the tiles here, these are our background tiles here in the second name table, or rather the second character ROM table rather. And then we've got our sprites set to use the first character table. And then these just show you the palettes I've got set up here. So the first 4 palettes are for the background clouds and the trees and grass, and then the bottom are for the Yoshi and the flapping sprites. So if I close that now, I'll show you the graphics for these things. So this is the screen here for the level, if you like. You notice that there is lots of reoccurring graphics here, which is why all the graphics for this level are literally just unique tiles. You don't obviously turn the whole of the screen into tiles, because there would be a lot of wasted space, plus there's not enough memory to actually do that on the NES. So when you create scenes from tiles, you can literally find duplicates and then just reuse them. So it's like creating like a big jigsaw puzzle. Although this video obviously isn't about tiles, but I'm just diving in here to quickly show you how it was made up. And then we have the flappy sprites here. Got 2 characters, got a bird here and a butterfly. The way that the palettes are laid out is that the black colour is always last, so we can interchange all of the palettes. So they take 2 palettes, and then Yoshi takes 2 palettes. So this is our Yoshi character here, built from 4 blocks of 16 by 16 images. These are the actual tile parts used there, and there's our 2 palettes there. So now that I've showed you the graphics, let's get into the code. So to start off with, I'll come to the main part of the code here, because I think this will probably need some explaining here. So one of the first things I needed to do here, if you enable 8 by 16 pixel sprites, then you also have to switch which graphics table they kind of use. So in this case, we've set the character ROM to be using table 0, bank 0 rather, and then this one here will turn off the flag to use the sprites as bank 0. By doing that, it enables us to use the 8x16 sprites. And then we also hide the left column. So always make sure that you have the NES include header there when working with the NES and GBDK. And then I have a number of different functions here to handle loading the tile data into memory. So the tile data here that we're using is in the format of the Game Boy. So it turns out there's actually a setting in the NES to switch the order that the tile data bytes are actually read in, and by having that set, which GBDK does for you, it allows you to use the graphic tiles of the Game Boy. If you've seen my video on the Game Boy graphics creator, or converter rather, you'll be all familiar with that. If not, then I'll recommend you check that one out to see how you can use LibreSprite to create some graphics which you can then convert into tiles, which you can also use on the NES as well as the Game Boy and Game Boy Color. The only difference is when you when we convert the graphics, rather, the colors I use here are actually set out in the style of the Game Boy Color, and the palette data that that the image converter gives you will be specific to the Game Boy also. So what you need to do after you've after you convert the images is look for the matching color in the NES palette. For example, these, when you create the images, try and get a color which aligns very similarly to the actual NES palette. Open that in LibreSprite, then we can control it a bit better. So these are these palettes here which I used. What I did first was, if you press I, then it brings up the eyedropper there, and then you can hover above a color, press the left mouse button, and then it will show you what the red, green and blue values of it are. So as that's 87, that's obviously not really a number that the Game Boy Color would work with, but 88 is. So if we look here, we'll see that that's 88. So design your characters using this palette first off, but then when you save it, align them to numbers of 8 so that they work with the Game Boy image converter. And then afterwards, where you've got the palettes, so in this case this is the Yoshi image there, so bring Yoshi back across here, you'll see we've got 30 as the first colour there, which is white. So there we go, that's that one there. Then we've got 9, which is that same green. And then black, which is 15. And then same again, white, and then the grey colour, and obviously the darker shade of grey there. So that's quickly going over designing the graphics there, like. So I'll close that out, and then the graphics define header is where I always lay out all of the external arrays and palette data arrays to load into memory nicely. So there's only 49 tiles that make up that screen, and then there's 16 tiles that make up Yoshi. So Yoshi will be at tile 0 in the sprite tile ROM, and then setting it out like this, we then have the tile starting position for the baddies tiles. So we can then use these two here to get the starting position for that, and then they take 16 tiles as well. So we only use 2 of the palettes there for the scrolling screen. And then another thing in this as well is the screen tile layout. So this map here represents each of the tiles on the screen, and using this map as a reference, this points to which tile to draw, so we can get all of the clouds seen. So that's how you would kind of build up a level in memory to copy across. Now into our utils function here. So we've got our custom data types to work with. These are from the tile attribute video still in here. This is something that we didn't use in here. This is something I was going to put in, but just allows us to work with 16-bit numbers easily, or rather signed 16-bit numbers. Then we have some familiar external variables to handle things for us nicely. We've got our tick timer structure and some functions to work on those, and then these are the same sort of functions from the last video for setting tile data and tile palettes. And then we've got the tile position one there, and tile put color, which also takes in an attribute byte as well, and some various functions that aren't used in this video for printing strings and such. So the key parts here I'll go over here is the sprite manager for you to use. So first off, we define a sprite maximum variable here, although we don't really sort of use that much in here. And then got a sprite initialization function here, just to set some things up for us, and then a clear function here which will hide all the sprites So to add a sprite, we just call the sprite add function with its horizontal, vertical, tile ID and its attributes byte. So in this video all I'll be using is the 2 bits that control which palette the sprite uses, and then I decided to have a separate function for setting its tile ID and then another one for its position. And then we have the 2 most important ones there for setting the tile data and setting the palettes up. So if I just jump into the code for the set tile palette here. So this palette command here obviously controls setting the background tile palettes. If you look on the NES Dev wiki, you will see that in PPU the palettes are all laid out sequentially in memory. So if you set palette 4, then that is actually palette 0 of the sprites. Hence when we look at the set palette command for the sprites here, I'm literally just adding 4 to the palette ID which is passed in, and then ANDing that value with 3 to create a mask. Probably not needed really. And then the palette count is just the amount of palettes of 4 colours that you're passing in. So this would only be a maximum of 4 here. And then this just utilises the same command here to set the sprites palettes. And then if you notice here, this sprite function here from GBDK is using the tile data GB here. So it's using the Game Boy tile format. So the initialize function here, what that's doing here is setting a private variable which handles which sprite ID. As there's 64 sprites, they all have a reference from 0 to 63, and there's 4 bytes associated with each sprite. GBDK creates an array which it updates for us in the background every time there's a vertical blank. So we can use the shadow OAM array to set the various bits for our sprites. And then GBDK will handle all of this stuff for us in the background. So we have to call sprite init first, because this then zeros the sprite ID and also the sprite count, because at the start these could be set to anything. And then if you look through here, you'll see the relevant parts here. So this works on 2 sprites at a time, as the sprites will be set to 8x16 mode at the start here. Obviously we could have just used the GBDK sprites command. However, GBDK does a load of stuff for us at the start. I'm not totally sure of everything it sets, so I do this myself just to make sure that the relevant bytes are actually set. So there's a load of shadow variables that GBDK has, which it updates when the display is turned on every vertical blank. So these are literally just convenient functions here to handle things for us, so we can concentrate on making the games rather than twiddling with individual bits each time. So this creates 2 sprites for us. It also automatically changes the tile ID as well. In 8x16 mode, there's obviously 2 tiles per sprite, so we have to add 2 to the tile ID we pass in each time. And then we also add 8 to the horizontal position of the first sprite. And update the sprite ID as well. And then this updates both of those in the background, so we don't have to worry about what sprite's actually being worked on at any time. Although we will have to remember which ID our sprites are assigned to, or rather the first sprite of each of the 2 for our 2 sprites which make up our 16x16 image. So these just handle a load of stuff for us in the background here. For example, the setting the tile here works on 2 sprites at a time, same as set the position as well. So let's get to the core of the program here. So because of the limited way that we have to work with the NES, we need to make sure that the display is always on when we set palette data. So we turn the background on first, show the background after we've set all the data, and initialize the sprites. This command here just clears the screen. Could have just had a clear screen function, really, like in the some of the other examples. So we set the palettes up, and then we have to set up how the sprites are laid out. So the Yoshi character, if I find the image here, it's not exactly laid out like this. So some of these parts need to be moved around. If we look at the actual tiles themselves, to get him looking like this, we need to move all these around slightly, which is why there's all various little offsets here to his horizontal and vertical position here. So those 3 parts make up Yoshi here. And then in the main loop here, we've got our input update function in utils, which we're working with here. So this handles updating our joypad bytes, which record what's actually happening to allow us to handle whether there's a key press or whether the key was pressed, as in what was the state of the last key pressed. Then we've got our update timer here, which is hard coded, unfortunately, here. So create 2 timers for this demo here. We have the animation timer, which controls when the character's wings flap and they change frames. And we've got the scroll timer here, so you can always play around with that. So there are delays in to slow this down, so it does move at a decent pace if you change these variables here. So the scroll timer here, when that elapses, we reset that and then scroll the background 1 pixel to the right, which results in the scene appearing to move to the left. And then in our animation update here, we have a variable which controls Yoshi's frames for flapping the wings, and we have another frame for the enemies flapping their wings. Then we have 2 update functions here, one for handling Yoshi and one for handling the enemies, or well, they're not really doing much in here, but let's jump into how they're handled. So we've got 3 variables for, well, a few more actually, a couple of variables there for Yoshi. We've got his horizontal and vertical position where he starts off at. Then we have 2 more Boolean variables here. So if you're working with these, you have to include standard bool in GBDK. And then our baddies have a number of different variables set up for them. Initially I did have an X speed variable in here, which I've decided not to use because otherwise they move around too fast, and I would need to kind of have a separate timer for them, which I wanted to avoid for this. So I'll get to our initialize function first for the enemies. So we have a byte here for the array ID, and these are the starting positions for them on the screen when they're initialized. And then we have a starting tile, which is for the first frame of each of them. Then we just iterate over a loop to create them here, set up their positions, use add the sprites which are associated with them. So you see there's also an array here for holding what sprite ID they are. We easily are able to get that from the sprite count variable. Then we update this X and Y variable here, which controls the starting position of the enemies. And then I just add 12 to the sprite tile starting number, or sorry, 8, so that we skip over the parts here. So if I show the grid here, we put that to 8 by 8 and then offset that by 1. You can see the 4 tiles there and another 4 tiles there. So to get to the second enemy, we have to add 8 so that we get to the top left starting position here. So by adding 12 here, this is the check to see whether we've gone past this tile here. If we only want to be either at this tile or this tile loaded in here. Hopefully that makes sense. And then our update here, have some more local variables at the start of this function to handle things for us. So we copy the X position into BX first, then subtract 1 from that, pop it back in, get the Y position into BY, add the speed to it, put it back into BY, see whether that's smaller than 8 or greater than 208, because obviously we want to keep it on the screen, and if it is, then we flip the vertical speed to cause it to bounce. what we do here is, as this frame ID is used for all of the baddies, we take that and times it by 4 using bit shift. Again, as there are 4 tiles here, to change to the next frame we obviously add 4 so we get to there. And then this then can be added to the tile start for each baddie. And then this just sets the position and the tile of the sprite. Obviously we use the sprite ID in the baddie array there to do that, and then iterate over all of the baddies. By all means play around, add some more, and if you change this variable here to add some more baddies in, you might need to increase this number here. There is no reason for it to be capped at 8, to be honest. This is copied from another program. The idea with all of these things is so we can just create kind of a library of useful functions to use as we need. And now we'll get to our Yoshi update bit here. So we've got our joypad handling part here. So if we if the right key is down, move right, set the moved flag to true. So the reason why we have the moved flag here is because if we move, then we need to update the position of all 3 of those 16 by 16 images for the sprites. And then we also have a separate part here for if the wing is flapped. So we only update the position and flap the wings when there's a change. And then we clear the changes out at the end here. So that concludes this example. Hopefully you will find all of this useful when working with the NES. I'll leave a link in the description to the video to point to the NES Dev Wiki, and I will also include again the palette image and the individual images I've used here as well, so you can have a play around with them, maybe redesign them slightly to whatever you want to use in your own programs. Right, that's it for this video.